In this chapter, we're going to talk about stoichiometry, which is the math of chemical reactions. We're going to start off by discussing doing problems where we convert moles of one substance into moles of another substance. Then we'll move on and expand that into things that aren't moles, so what happens if I have grams, or if I want liters and stuff like that. We'll talk about limiting reactant, which is what happens when you have one substance that runs out and one that's left over. And then we'll finally get into a discussion of percent yield, which is talking about how much of a reaction actually occurred compared to how much it could have made if all of it had reacted. You are going to need a pencil, you're going to need something to write on. A calculator might be helpful for the upcoming videos. You'll want your periodic table. So once you have all those ready, let's start. Okay, so like I said, stoichiometry is just the mass relationship between the substances in a reaction. So the idea is that if I give you a balanced chemical equation, and I give you one amount of one substance involved in that reaction, so if I said, for example, 10 grams of sodium react, you would know how much of everything else is involved in that reaction. So if I put sodium in water, for example, you could figure out how much water is involved in that reaction, how much sodium hydroxide is generated in that reaction, and how much hydrogen is generated in that reaction, all from knowing just one amount and having the balanced equation. Now, the way we're going to do this is we're going to look at the equation of the reaction. Specifically, we're going to look at the coefficients. So if we take a look at this equation right here, this is the combustion of propane. We have to remember that the coefficients are not only the number of molecules that are involved, but they're also the number of moles. So 1 mole of propane will react with 5 moles of oxygen, producing 3 moles of carbon dioxide and 4 moles of water. Right? So 1 mole propane, if it burns, will produce 3 moles of CO2. Now, if I started with 4 moles of propane instead, how much CO2 will I make? That's just a proportion, right? If 1 makes 3, then 4 is going to make 12. So 4 moles of propane will make 12 moles of carbon dioxide. Now, similarly, let's say that I had 10 moles of oxygen that reacted. If 10 moles of oxygen reacted, how many moles of water are we going to produce from that? Take a second and figure that out. Okay, so in the equation, 5 moles of oxygen make 4 moles of water. So 10 moles of oxygen, which is twice as much, will make 8 moles of water in that reaction. That, in effect, is all that stoichiometry is just using those coefficients as a conversion. Speaking of the conversion, the type of conversion that we call this ratio is we call it a mole ratio. Right, so the mole ratio is just a conversion factor written from the coefficients of a balanced equation. And the way that you always write them is you always write it as what you want on the top and what you're given on the bottom. So you'll say 3 moles CO2 if that's what I want. And then on the bottom I would say either like 1 mole C3H8 if that's what I was given, or 5 moles H2O if I was given water. So that's the mole ratio. Again, just make sure you write it correctly. It's always going to be what you want over what you have. And the reason why this mole ratio is important has to do with how the stoichiometry process works. Stoichiometry is a mole-to-mole conversion at its heart. So to do any stoichiometry problem, regardless of what I give you, you start off with the number of moles of what you're given, which you may have to do a mole conversion to get there. Multiply it by your mole ratio, and that will give you the number of moles of what it is the question's asking for. Right? So at its worst, you do a conversion to get your given substance into moles, multiply by the ratio that we just went over how to make, and that will equal the number of moles of what you're looking for, and from there you can convert it into whatever unit the question's asking for. Right, so let's try a quick example of this. So we have the decomposition of potassium chlorate. 2KClO3 yields 2KCl plus 3O2. If 9.3 moles of potassium chlorate decompose, how many moles of oxygen are we going to make? Pause the video, try to set it up just like that last example showed us, and when you think you have an answer, pick it back up and we'll go over it. Okay, so our starting amount here is 9.3 moles, KClO3. Notice I'm going to write the number, the unit, and the substance because I want to know what substance I'm working with at that given time. So 9.3 moles KClO3. Since it's in moles, I'm going to multiply by the mole ratio. I want oxygen, so O2 will go on the top. I'm trying to cancel out KClO3, so that will go on the bottom. 3 moles of oxygen is the same as 2 moles of KClO3. KClO3 cancels out. I'm left with moles of oxygen, which is what the question is asking for. So I just do the calculation and I'm done. So 9.3 times 3 halves to sig figs will give us 14 moles of oxygen. That's all stoichiometry is. Like I said, you may get a mole conversion at the beginning and a mole conversion at the end, but that's pretty much the overall method for how to solve these problems. In the next video, we're going to go over what happens if I don't give you moles and if I don't ask for moles, and how we do those. So like I said, just plugging in the mole conversions at the beginning and end. And I will see you guys next time.